Okay, so this is where we were up to from last time, that we were looking at spinning up this particular nucleus from the ground state, where this is just pure collective rotation, and we see a backbend due to neutrons, protons, and then eventually we reach the situation here, which we call band termination, where we've broken essentially the 6 pairs of the valence particles here, and they sort of go in equatorial orbits, and then all of the angular momentum comes from the single particles here. Then we also talked about how to go beyond these states, and we saw that there were some very high lying, it costs 1 or 2 MeV to go to these states here, and these represent the case where we've actually essentially pulled out another pair of particles from the core and aligned those two. So now we've got an extra 2 particles in essentially these orbits, these sort of like rings of Saturn here. So that's how we can go beyond these special states, but it is energetically expensive. So is there a way that we can actually go to even higher spin over here? And well, yes, and that's what we're going to talk about today. Because what we found in this nucleus and its neighbor, it's a nice example of a really long sequence of regular space gamma rays, and these we think just correspond to the rotation of a well-deformed shape. It's a sort of super deformed type of shape, so it's much larger moment of inertia than the ground state, for instance. And so if we adopt, or if the nucleus adopts this really elongated shape with large moments of inertia, it can then just spin up or to much higher angular momentum values here. In fact, we think this probably goes up to about spin 65 or even higher, maybe 70. So this is going way beyond the band termination, which would happen, well, we mentioned 46 plus was the typical value. So now we can sort of bypass the band termination if the nucleus adopts this shape. Now this is very weak, this structure. For instance, if we want to compare it to the super deformed band in dysprosium, so this is one of the first examples of such a nice structure. Well, this thing here is 100 times weaker, so it's very difficult to actually pull out this spectrum, and it had to make use of multiple dimensional coincidences between gamma rays that come off the nucleus. So where does that sit on our diagram? Well, it's this structure here. So this is our new band, and we call it a high moment of inertia, and we think it's a triaxial, strongly deformed shape. So triaxial means that all 3 principal axes are of different lengths here. So it's a squashed prolate shape, kiwi fruit or a potato is this sort of shaped thing. Now if we look at this inset with our beta gamma or epsilon gamma plot here, this is where we started at low spin, and then we go over to the terminating states here, and now this new shape of the nucleus would sit somewhere here. So notice it's much bigger deformation in terms of epsilon, and it also has some finite value of gamma. So it's somewhere in the middle of 0 and 60 degrees, so maybe 30 degrees or something. So this here represents this elongated shape, and then if we plot the energies of its states, this is what we find. So now see, this sort of bypasses the terminating states, and then at very high values of angular momentum. This is becoming the favoured configuration here. So notice once we're into this configuration, then we would essentially decay down it all the way to the bottom, and then at this point we would have to decay into the other less deformed states here. And you can see there's a big energy difference here, and it's difficult to actually see the decay between this structure and the lower spin states here. So this now takes us up to well, at least beyond 60 H-bar here. Now sometimes this is called the ultra high spin region. So what's essentially happened as we go from spin 0 up to spin 70, as we start with a prolate nucleus, it becomes oblate in the middle here, but then at the very highest spins we have this triaxial shape. So that's what's shown here: prolate, oblate, and then it becomes triaxial and elongated more than the other cases here. And again, let's just look at super deformation here. We originally defined super deformation as when the major to minor axes of the prolate shape exist in this ratio of 2 to 1. So the long axis is twice the length of the short axis. And if we plot essentially the energy here, or potential energy, against the deformation, this is what we would see. So first of all, let's look at 0 H-bar, so low spin, or the ground state. This is our potential. Notice it has a secondary minimum here, but this is the deep minimum, and this is where we would expect the nucleus to sit at this sort of deformation here. Now let's have a look at the potential if we go up to spin 60. So what happens is now this secondary minimum, because it has a larger moment of inertia, actually comes down in energy, and you can see at this point it's actually sort of at the same level here, so it's competitive. And so if we can form the nucleus in this state here, so with very high spin, it may get trapped within this secondary minimum. And so this minimum here has a much bigger deformation, and that is the super deformed shape. So when we create these nuclei, it's usually through fusion reactions, and we bring in a lot of angular momentum, 60, 70 H-bar. So that's where we would create the nucleus, and then it could get trapped here. And then once it's stuck here, as it slows down, it will stay here. Essentially, it'll come down, and at some point, then it must try to decay over to the lower deformed states here. So this is the idea of super deformation. There's this secondary minimum in the potential energy surface. I think I've shown this previously. So one of the first cases of a super deformed shape was in dysprosium 152. This was work done, I think, in the mid-80s, Daresbury. That's sort of midway between Liverpool and Manchester. We used to have an accelerator there so we could produce these nuclei in fusion reactions, and this is a gamma ray spectrum of this case. So again, it's a very regular structure, and the spacing between each gamma ray is relatively small, pointing to a large or enhanced moment of inertia and shape. And so if we look at the what we define as super deformed, this 2 to 1 axis ratio, what this means is our shape parameter beta, for instance, is this number here, 0.6. Now, in a typical nucleus at low spin, this is more likely to be 0.2. So that's a typical value of the quadrupole deformation of a nucleus. But this one is much larger and is, let's say, associated with this special shape with a 2-to-1 axis ratio. Now, in this nucleus, again, if we look at the spins, we can see that here, again, we have to go up to about a spin of 60 h-bar at the top of the band here. So actually, I think this might be in one of the tutorials or homework questions. Let's just look at some of the numbers associated with that particular band in dysprosium. So it consists of about 20 gamma rays, and we know essentially we know the lifetimes of the individual states, and we know that to go through the bands from the top to the bottom takes about 10 to the minus 13 seconds. And we can also add up all the gamma ray energies, and this is about 20 MeV. So essentially, in the decay through that structure, starting from spin 60 down to about spin 25, that there's 20 MeV gamma ray energy released, and it occurs in this short time. So if we just take the ratio of that, this is just the power. And if we convert that into SI units, no, this is like 32 watts. So this is like a dim light bulb. So that's the amount of energy that is released just decaying through that rotational structure in the nucleus. Something else we can work out, we know that the rotational frequency is half the gamma ray energy, and a typical gamma ray energy is about 1 MeV. So we can say then that a typical rotational frequency is 500 kV, or at least h bar omega is that value. In other words, that the rotational frequency is about 10 to the 20 or 10 to the 21 radians per second, and this would convert into 10 to the 20 hertz for the number of revolutions per second. And what that means, in just decaying through that sequence of gamma rays, the nucleus actually performs about 10 to the 7 rotations. So given this frequency and the time scale, this is where this comes from here. And it's just interesting for comparison, this is the same as the number of days, of Earth days in 30,000 years. So that's how many rotations the nucleus has done just passing through that band. And the other thing about this particular band in dysprosium, at the bottom, it actually passes through a very long-lived state, isomeric level. So this has a much longer lifetime, usually by orders of magnitude, than a typical nuclear level. So instead of 10 to the minus 13 seconds, if we consider now the lifetime of this bottom state, this would actually increase the number of rotations up to something like 10 to the 12 rotations before this state decays. And to put that into perspective, this is typically the number of Earth days since the Big Bang. So that's how many times the Earth would have rotated in that time. So these are just then some typical numbers associated with a rotating nucleus, especially in one of these nice super deformed shapes. Well, we talked about dysprosium. I think I should show this one as well. This is a cerium. This is another example of a super deformed band. It's arguably the first one ever seen, and this was also done at Daresbury by people from Liverpool here. There's a bit of an argument here because we think this corresponds to a 3:2 axis ratio, and so is that really super deformed in the sense that we called it a 2:1 axis ratio? But nevertheless, this is still corresponds to an enhanced deformation. It's much bigger than essentially the ground state of the nucleus or of a typical nucleus here. And again, we can say if we follow the band up to the very highest gamma rays, again, we're approaching something like 70 h-bar in the nucleus. And again, this is about the highest spins that we've ever seen. And just to show you that these are super deformed bands, or bands with enhanced deformation, do occur in several regions of the chart of the nuclides here. So we talked about dysprosium, that was dysprosium 152, so that's in this sort of region here. And then I showed you the cerium, which is in this region here. But then we also see evidence for nuclei round about mass 190 or 240. There's also evidence for these super deformed shapes. And then also there's some lighter region here, 80 particles. There seems to be some evidence for very deformed rotational structures. So we should also mention then these super deformed shapes in the nucleus coexist with other shapes. So let's go back to the dysprosium 152. So first of all, this is the sort of the normal level scheme here, and if you notice, it's not very regular, and it more or less corresponds to a weakly deformed shape. Essentially it's sort of spherical with a few valence particles around, and that's how we would generate all these states here, but there's no sort of regularity seen. Now, the super deformed bands we talked about would be here, and in fact there are multiple bands now known that seem to correspond to the super deformed shape. So this is our really strongly deformed 2:1 axis ratio. So this is how the nucleus then generates the very highest angular momentum. And then at some point, essentially when we get to the bottom of the band, there has to be a decay. These are quite high energy. I think they're about 4 MeV gamma ray transition energies that come and feed the low spin part here. Now it turns out in this nucleus that there are also another set of bands which are deformed, more deformed than essentially the ground state, and we think these are triaxial. So there's sort of modest deformation, but with a triaxial shape. So that means that the 3 principal axes have different lengths, but these can also form rotational structures. And the main difference between these triaxial bands and the super deformed bands is in the moment of inertia, or the spacing between the gamma ray energies here. So these are all closer together, implying large moments of inertia as compared to these ones here. But this is just a nice example of where we can essentially have 3 distinct shapes in the same nucleus, and they actually essentially compete to build up angular momentum. Now, we've been talking about super deformed shapes, but in principle we might also expect a hyper deformed shape which would have a 3:1 axis ratio. And again, if we plot the potential energy here as a function of deformation. This is what we would expect. So we have our low deformation normal states, then we had a second minimum, and this is where the super deformed shapes would come in here schematically, but then there may be another one here, a third potential minimum or local minimum, which would correspond to a really elongated shape, or the hyper deformed shape here. So presently that we have now many examples of a super deformed shape, but so far we've not found any examples of the hyper deformed shape here. So just to mention how much angular momentum can the nucleus hold before it would fission. So if it rotates fast enough, it will eventually fly apart. And this shows here essentially what this angular momentum is, a critical angular momentum. So as you see here, it's 80 to 100 or 95 value. So that would be the maximum spin that the nucleus can hold before it fissions. And this is also plotted as a function of mass number here. So you see nuclei with this number of particles. So for instance, this could be the cerium and dysprosium nuclei there, so somewhere in the middle, and they can actually accommodate the highest values of angular momentum before fissioning. And we've mentioned that we may be up beyond 60 h-bar now, approaching 70, so we're not that far off the limit before the nucleus will just fission or fall apart. Now, one interesting thing here is in sort of classical physics, if we rotate something just before it fissions, we sort of go into a region at the very high spins called a Jacobi regime, and this is where we would have really distorted triaxial shapes. Again, this would mean that the principal axes of the shape are different. So as I said, this is mainly coming from classical physics. Now, if we look at some asteroids, they seem to have a strange triaxial shape. And this is an example here. I think this is an asteroid called Ceres, which actually gives the name to the cerium. But this is a classical body that's adopted one of these Jacobi shapes. So it's a very distorted prolate shape, but it's also squashed, so that it's the triaxial shape. It's the kiwi fruit type of shape. And so this is actually a solution in the classical mechanics for a self-gravitating fluid of uniform density. So people first thought that this would adopt a sort of spherical shape, but then found that a sort of consistent solution has this special triaxial shape with all the principal axes of different lengths. So this is what we think could be happening in the nucleus as well, at the very highest values of angular momentum. Now this is interesting as well. This is a piece of moon rock brought back by one of the Apollo missions, and you can see this looks like it's been rotating extremely fast, and it's sort of on its way to fission. So this is also like a nucleus. Notice it's thinner in the middle, so this must have been rapidly rotating, and the two ends were about to sort of split and fission. So this shows that this rock must have been spinning extremely fastly in the universe, and then it sort of condensed and solidified and maintained this shape here. So this is sort of going beyond the Jacobi shape and going off to essentially almost a fission here. So again, see, these are very large macroscopic objects that behave similarly to the nucleus. Again, just to show you, galaxies, another example of things that rotate. And what's good here, or what's interesting here, if we look at a rotating galaxy and then try to measure the rotational velocity as a function of the distance from the center of the galaxy, this is what we get here. So this is the curve. Notice it sort of flattens out here, which is unexpected. And for a galaxy that looks like this, we would expect this behavior here. And so what's happening here, this is sort of suggesting that there's a lot more mass associated with the galaxy here than we actually see. And this is evidence then for dark matter. There must be something here, very massive, a part of the galaxy that's causing this rotation curve to follow this form here. So there's essentially some missing matter unobserved associated with the motion of this galaxy. And I think just to finish off then, we can just look at systematics of rotation here. So this is just the typical size of a system plotted against the rotational frequency, if you like, number of revolutions per second. So we can start off here from galaxies such as the one just shown, Andromeda, go through other sorts of large scale objects, get here. So this is like a skater who can spin in an ice rink, and that's where they would sit. And then if we go up to our nuclei, we would sit here. So this is our rapidly rotating deformed nucleus with about 10 to the 20 hertz in terms of the rotational frequency here. And then only beyond this, I suppose we could look at substructure in nuclei to get to actually even higher rotational frequencies and actually a smaller size of the system here. So essentially the smaller the system then, or the dimension of the system, the higher the rotational frequency can become. So I'll stop at this point and we'll go on looking at a different type of high spin behavior next.